Hi everyone, we are the team from the University of Virginia. Today we will be presenting our stormwater design called Reviewing Runoff. But before we begin, we wanted to start out by thanking you all for still hosting this competition. We're very appreciative for the opportunity to compete and learn from our peers, so thank you. My name is Hanya Abud, I'm a civil engineering major.
Hi, my name is Ekaterina Forkin. I am a systems engineer.
My name is Jason Jabor. I'm a systems engineer.
And I'm Anna Liang, and I'm majoring in environmental science. For our proposal, we wanted to tackle the issue of stormwater and how to improve the way our current drainage system responds to stormwater. This is a particularly important and relevant issue because of the increasing urbanization in Charlottesville City. The University of Virginia is located in the heart of Charlottesville, giving us the perfect opportunity to improve upon this issue within the bounds of our own community, while also impacting the Charlottesville community at large. This stormwater life cycle diagram helps illustrate the journey of stormwater and how urbanization has posed a major issue to surrounding habitats and species of wildlife. Because of urbanization, there has been a strong increase in impervious surfaces, totaling 99 million square feet in Charlottesville City alone. This leads to increased rates of stormwater runoff that can't soak into and absorb into the ground. This overwhelms drainage systems and causes flooding, negatively impacting the infrastructure as well as the community. As the water travels to drains, it picks up pollutants, such as gas from cars, fertilizers, or pesticides, and the water acts as a mechanism to transport these pollutants directly into local watersheds. Because there aren't any intermediate treatment water facilities, this is a particularly important issue. So through our current drainage system, stormwater is drained directly into local watersheds like the Rivanna River and connects to larger bodies of water. This increase in stormwater runoff, which carries pollutants, also increases the pollution in the watersheds, and increasing the amount of pollution in the watersheds causes a multitude of negative impacts, such as excess nutrients from fertilizers entering waterways and the erosion of waterways. Ultimately, these impervious surfaces lead to negative impact on aquatic habitat and wildlife because of things like eutrophication, algal blooms, and sediment loading. With our proposal, we wanted to emphasize how local practices contribute to systemic issues. Currently at the university, there are not many best management practices or BMPs on grounds. When we came up with our proposal, we were trying to create a smaller scale improvement, something that's realistic and feasible, but ultimately we wanted our solution to educate the public on BMPs and to set an example of how individual actions have global implications. We wanted this to be a learning experience about how local, regional, and global issues are interconnected. As seen in the pictures, the Rivanna River is a local watershed which feeds into the Chesapeake Bay, which is regional, and feeds into the Atlantic Ocean, which has global implications. So you can see these are three very different spatial scales, but they're all very much related to each other.
The chosen site serves as an aesthetic refresher for students and faculty. It is one of the few stretches of greenery within the engineering sector. The walkway area is located between Thornton Hall, which houses the main engineering wings, and Olson Hall. There are multiple drainage systems in the courtyard, which are reflective of the same issues in the regional drainage systems. Some current stormwater management techniques are cisterns and rain barrels, which are used for lawn and garden irrigation. Our campus also has several biofilters, which are a pollution control technique that biologically degrade pollutants. However, there are not enough to cover the entire campus, let alone the engineering sector. Additionally, there are a couple infiltration trenches, but they are not located on central campus areas. Lastly, there is some permeable pavement, but it is not placed anywhere near the site and is only located on two peripheral school properties. The drainages at this site directly deposit runoff water into Meadow Creek, which drains into the Rivanna River. Thus, it is critical to improve the quality of the runoff stormwater caught from the site. Notably, decreasing the pollution fed through this local drainage system will lower the university's overall pollution runoff by decreasing its total maximum daily loads. An observational study followed by coordinate and topographical point collection was completed. There's a fairly steep slope on the eastern side of the site that often floods during high precipitation. One major takeaway was the lack of low-impact development BMPs.
So before we began designing a solution, we wanted to outline what our overarching problems were. So we thought about it and we came to two overarching problems. The first one being quantity. So as my teammate Katya mentioned, there is some steep topography, specifically on the eastern side of the site, as well as many impervious surfaces. And because of that, we have a large amount of water draining off of the site. The second problem that we outlined was the water quality. So the site currently has a traditional stormwater management system, and traditional stormwater management focuses on removing as much water as possible, as quickly as possible from the site to provide flood relief. Now, the problem with that is that it doesn't actually increase the water quality, therefore directly dumping pollutants and nutrients such as phosphorus and nitrogen into local watersheds. So at our site, as Anna mentioned, we're dumping pollutants and nutrients into Meadow Creek. So we wanted to implement best management practices, which would improve the quality of the runoff, therefore reducing the damage done to local ecosystems. So like I mentioned, we had quantity. And so the way that we wanted to address the quantity problem was increasing permeability, as that would reduce the amount of water running off the site. So implementing permeable pavers, increasing vegetation, as well as other BMPs. And then for water quality, we wanted to remove pollutants at the site, therefore reducing the amount of pollution entering Meadow Creek and increasing the water quality. Now we wanted to get a numerical sense or representation of what was actually happening with the water on site. So we modeled the site and we put it into Civil 3D. And we used the water drop analysis feature. And so that gives you an outline of where the water runs when you have a stormwater event. And then using those path lines, I think you can see them in light blue, we outlined 3 catchments where the water pools. So we have them outlined in pink. We found the area of those catchments, and we also calculated the runoff coefficient of the catchment. So using that information, we conducted a rough estimate using the rational method analysis, and that gave us a rough estimate of how much water was running off the site. So that is the Q value, which is peak runoff rate in cubic feet per second. When we conducted this analysis, we used 2 different assumptions. The first one was that the storm event would be a 100-year storm. And the reason that we selected a 100-year storm is because due to climate change and global warming, we're seeing an increased frequency of catastrophic storm events. We're also seeing more dramatic storms, more rain, as well as changing weather. So we wanted to make sure that our design was ready to withstand such kind of events. And the second assumption that we made was a time of concentration of 5 minutes. So then we calculated the Q value for the overall site to be 1.096 cubic feet per second. Now, in order for our design to be proven productive, our post-analysis should have a decreased Q value, as that gives a numerical representation of an effective design.
So what exactly do we want to accomplish? Ultimately, we want to decrease stormwater runoff, and lowering the runoff coefficient would directly reflect such a goal as Hanya just mentioned. This is done by increasing permeability of the catchment areas. Next, runoff water quality must also be increased, and integrating BMPs would reduce the number of pollutants in this runoff water. Lastly, any proposed solution should align with EPA standards and stay within feasible university budgets.
So with these design goals in mind, our team developed practical, efficient, and a low-cost solution. And we achieved our goal through the implementation of several best management practices, BMPs for short. Okay, so from the water drop analysis, you saw that the majority of the storm water flows to the eastern portion of the site because of the steep slope and existing storm sewers and pipes. And the areas that we observed were near the end of the runoff path where all the water runs to. We placed a bioretention system made up of 4 rain gardens. And a bioretention system is crucial because it removes contaminants and sedimentation from storm water runoff. Rain gardens also reduce peak outflow and remove up to 90% of chemical pollutants through phytoremediation. They're comprised of several layers, one of which is a grass buffer strip, which reduces the runoff velocity, and phytoremediation plants that uptake pollutants from the runoff. We recommend using 3 specific plants in our rain garden because of their nature to uptake pollutants and live in moist areas. And the 3 specific plants that we chose were the Joe Pye weeds, blue lobelia, and rose miltweed. A picture is worth 1,000 words, so here's an illustration to help explain what's going on. Up at the top of the illustration, you see Thornton Hall, and then our steep elevation, or hill, and at the bottom is the rain garden that we're implementing to catch all the runoff. A 10,000-gallon cistern, underground cistern, is proposed to be installed near the eastern side of the site. And it's specifically selected to be placed here because of the path of the storm sewer drains that already exist on the site. So no additional excavation would be needed or any additional piping. Unlike rain gardens, cisterns are not powerful pollutant removers, but cisterns do collect runoff water and in turn reduce the runoff volume. They also facilitate recycling of water because they store water, and then after a storm has passed, the site can reuse that water to irrigate the site. And it also preserves the aesthetics of the site because it's placed underground. Here's an illustration of what I mean. We use a translucent surface to show that the cistern is placed underground here on our hill. The current site has a large area covered in traditional cement sidewalk, and traditional pavement has an extremely high runoff coefficient of about 0.9. And because of this, we elected to replace the existing traditional pavement with permeable pavers because they have a phenomenal runoff coefficient of 0.3. Benefits of this include reducing the runoff coefficient, of course, and erosion. Here is a picture to better clarify what I mean. Instead of traditional pavement sidewalk, we will be using permeable pavers. As we spoke earlier, the UVA drainage system is not connected to treatment facilities, and the pollutants from the site run through the runoff water, flow through the runoff water to nearby watersheds. And to improve the runoff quality, our team is proposing the addition of media filters to be installed on 2 drains that already exist on the site. We specifically recommend using a media filter such as a Filterra unit because they're small, pre-constructed, and remove up to 55% of phosphorus from runoff water. And here's an illustration of our site. The gray boxes show these media filters that we're adding. We're also adding an electric scooter charging station as shown in the yellow to encourage environmentally friendly transportation, along with some solar-powered streetlights. So, okay, cool. But up until now, all of these solutions have been theoretical. So we wanted to test their actual viability to implement on our site. And to do this, we produced some alignment profiles of each BMP to account for elevation adjustment. And the elevation adjustment will require a certain amount of cut or fill to be added or removed from the site. So by doing so, we produced a cut fill report, which showed that there's a very minimal amount of fill that's required to be added to the site. And this minimal amount of fill demonstrates the efficiency of our proposal, both economically and design-wise. Also, our pre-construction runoff coefficient was about 0.48. Post-construction, it significantly was cut in half by 0.23. Using this post-construction runoff coefficient, we calculated our new peak runoff. Pre-construction, it was about 1 cubic foot per second. Post-construction, it was also significantly decreased to about 0.5 cubic feet per second. And also like to point out that in the future, we plan to estimate the phosphorus load reduction by taking water samples of our site. That way we can get a better understanding of how we're improving the phosphorus runoff.
To further prove the feasibility of our proposal, a cost analysis was completed. These costs will be minimized wherever appropriate, such as using the cut soil for filling, as Jason just mentioned. Average costs for each proposed change were researched. Based on the quantity recommended, the total price for each expenditure was calculated, as seen in the final column on the right. While the price range is wide, the overall cost is low for the amount of positive environmental impacts our proposal will induce. Additionally, we conducted research on sources of funding. Notably, the EPA has two programs, the P3 and the Environmental Education Grant, through which college students may obtain funding for eco-friendly initiatives. Implementation of our proposal will be broken up such that the walkway is not obstructed for daily use by the community. Primarily, it should not inconvenience any roads between classes or become an extended eyesore. To ensure bacterial growth is minimized, the cistern can be chlorinated once a year to maintain cleanliness. The filters require minimal maintenance in the form of an annual inspection, which is simply necessary to remove seasonal debris like vegetation, sediments, and mineral salts. The installation of rain gardens and river birch trees create a more user-friendly environment in the courtyard. Next, the permeable pavers require annual or semi-annual checks to ensure that they properly filtrate. Essentially, this means that standing water should not be present following storm activity if the pavers are properly functioning. These phases are implemented such that they work upstream to downstream. We don't want to dig and then put sediment through BMPs that we had just installed.
Here is a walkthrough animation of our 3D rendering. This is the site and Thornton Hall. And as you walk through, you can see the electric charging station for the scooters. And here is our first Filterra unit. We can get a better look at it when going underground. And as we travel across the permeable pavers, we see our second Filterra unit, as well as the 10,000 gallon cistern. And lastly, the rain gardens. Like I mentioned in the beginning, we wanted this proposal to have a long-term impact. 4 focus areas of UVA's 2016 to 2020 sustainability plan include awareness, education, social impact, and equity. When we reached out to community members, a biomedical engineering student emphasized how our current drainage system inhibits her daily life. In order to positively impact the community and expand awareness and education, this site will have an informational display that students, professors, and community members can walk by and learn about. In addition, this will serve as a living classroom, right in the location where students are learning about this very topic. In the graphic on the left, we projected our site post-construction. There is an informational display describing the changes made to the site and the importance of best stormwater management practices. There are rain gardens using local flora and new shady study spots for students to take a refresher from being inside and in classes all day. We propose not only a small-scale fix, but a long-term solution which will positively impact the community and university for years. We would like to thank our mentor, Dr. Brian Smith, and the facilities management, Stephen Dempsey and Dawson Garrett, for helping us with the feasibility of our project, and Gail Hayes, who also helped us very much with the feasibility of our project. Thank you for listening.